Who am I? My name is Jeroen Domburg. Sprite_TM is my handle. I work for Espresso, although today I'm not doing anything with our chips. And my website still is spritesmods.com. Okay, so you have a thing here. It's slightly different color. The logic is this is we bought this for a little one. You can press the red button, and then you can say anything. And if you then press the big button, you'll repeat it. Easy peasy. Pretty cheap. We got four for, I don't know, some amount. Unfortunately, a little one wasn't that interested, let alone in four of them. So you do obviously what what all of you do. This is logical. I don't understand why the rest of the world disagrees with me. Open it up, see what's in there, see what makes it tick. Well, this thing has a few things. I mean, the most obvious thing is that the blob in the center, which contains who knows what. There's this little chip, and even the fact that I'm here, that is something well known. It's a flash chip, 25Q040 like. So SPI flash, 512K byte of flash, and obviously we're interested in what the hell is in there. So, a little bit later we desoldered. Strangely, the epoxy was actually under the chip. So seemingly the way they make it is that they first stuff all the things and solder it on. And only then they put on the die in the center, do the wire bonding, and then blob the thing. I didn't know that. I thought it would be the other way around. Oh yeah, the thing will change color every now and then. Sorry. I've worked on two of them. So, I do the usual thing. I desolder the flash chip. I try to solder some wires to it to put it on a header so I can easily put it on my flash programmer. And then obviously I also need to put it back. So I solder a bunch of wires to that thing. And obviously one of the pads of the stupid thing. So I need to epoxy it in place. And I was there and I'm like, oh crap, now I still need to connect a logical analyzer to it. And I've been here before, like many a time, and it still is frustrating. Like, okay, I want to have something else. I want to have something that can just use an interposer, a little bit of PCB that I can solder between the flash and the actual thing. What I want to do is I want it to be able to read the flash. I want it to be able to write the flash. And I also want it to effectively replace my logic analyzer so I can sniff the data that's going on. And ideally, I'd also have a little bit of tooling so I don't have to, go to the thing, press record, do the thing, and figure out where the stupid signals are, and then do the logic analyzer decode thing, figure out how to export it, and then figure out what the CSV format is again, because I forgot. I just want to know what the hell is going on, and I want to have that easy. Oh, and if possible, there's also something called a time of check, time of use attack. So I kind of sort of want that as well, if possible. What that means is that some chips will run either hash or CRC or something over the contents of their program before they actually execute it. If that hash or CRC or whatever does not check out, they think that the flash is corrupted or that someone bad is messing with that. You'd think that. And they will just refuse to start up. So what you can do is, with a bit of luck, they will only check that at startup. That is the time of check. So if at that point you present like the original flash content, they will go like, yes, everything is still in order. And if you then somehow change the content of the flash, when they actually use it, the time of use, then they will still happily execute whatever's there because they checked it earlier and it checked out, right? And Flash doesn't just change under your eyes. So yeah, I wanted to be able to change the Flash or at least a few bytes here and there that I can patch. There are solutions for this. This is one of them made by Tremel Hudson, I think. This is an existing dev board, ULX3S. It has an FPGA on there. Okay. An ECP5. It has a bunch of SRAM in there. It's got a bunch of more crap on it. It probably does what it needs to do, but I don't like it. the issue is that, first of all, it's the dev board. There are still wires going on that I need to solder. I don't like that. Secondly, this dev board is not very cheap. And third of all, this, because of the fact that it uses SDRAM, it is not very fast. It might be just the way the gateware is built, but this thing is spec'd up to 20 megahertz. And if I recall correctly, the camera that I hacked before already was 25 megahertz, so can't do that. Going over that, it's not. The other downside is that it only emulates one type of flash, and I wanted to just use whatever flash is in there. That's the reason why I don't want to use it. The dev board is fairly expensive and unwieldy because of the wires that are going on. So I'm going to build my own. I'm going to use this as a start. A cute little FPGA, ICE40UP5K. Has give or take 128K plus some extra of RAM. There's enough LUT so you can put a microcontroller in there. And it's not that expensive as far as FPGAs goes. $7, or if you put your trust in Taobao, you can get a bunch of working ones for $5, and you probably can get a bunch of working but not necessarily new ones for even less. Okay, schematic, that's not readable. It doesn't matter. FPGAs here, KiCad splits it up in blocks because otherwise it would be too unwieldy. There is a power supply here in the form of an LDO, 3.3 volt, 1.2 volts. FPGA needs both. USB, that powers the LDOs, obviously. USB is also the main connection to the host. So there's also a bunch of wires running directly to the FPGA for a USB connection. I am pressing the wrong button again. Oscillator, 12 megahertz. Within the FPGA, that is PLL'd up to 48 megahertz, but that's only because the USB needs it. Otherwise, I don't use it. Flash, the thing needs flash itself as well to boot from and to store the user program in. And this is the connector to the FPGA and what I call the DUT. This is the connector to the flash and the DUT. DUT is the device that flash was in, device under test, plus a whole bunch of ESD things because I don't want to kill anything because of me being stupid. Oh, and finally there is a little switchable 3.3 volt, 1.8 volt power supply. And the idea is that you can change the bank that these things are connected between 3.3 and 1.8 volt and the flash as well. So it's compatible with both 3.3 volt as well as 1.8 volt. Oh, finally, a bunch of LEDs. You always need LEDs. PCB, it's a 4-layer PCB, not shown are the ground plane and the power plane. There's a few traces running around on the power plane.
Running yourself?
Yeah. I mean, it's KiCad. You have a schematic, you have a bunch of lines, and then you just run traces until there's no more lines.
You're your own auto-router.
I mean,
don't trust auto-router.
Yeah. But like, also, this is the fun bit.
Yeah,
it sits and it's very zen, and why the hell would I let an auto-router? Come on. It's like you build an artificial intelligence in order to be creative. Anyway, interposer board. It has pads here that go to the original place where the flash was. You can mount the original flash on here, and this is the connector that goes off to the main PCB. The idea is that these interposer boards are more or less throwaway. As soon as one is soldered in place, you could technically recover it, but that doesn't really make that much sense. They're not that expensive anyway. So a week later, JLC PCB has done its job, so this is a drawing how it looks, and obviously I did everything correct the first time. But it's an FPGA. All pins are interchangeable, right? So you can just route it through. Few things. Turns out the FPGA core does not run on 3.3 volts, which I figured out after I got a very hot FPGA. It still survives, so there's that. The other wires are because seemingly clocking is weird in that you need to put a clock on a certain thing in order to use a certain PLL. And if you use a PLL in some modes, then you can't use some pads in input mode anymore. Yeah, I needed to rewire a bunch of crap. I technically have a V2 that has all the things correct, but I'm not sure if I'm ever going to build it or just going to live with that. Okay, it's an FPGA, so it doesn't do anything by itself. It does even less than a microcontroller. So it needs an SoC in there. So I built an SoC. Middle is a RISC-V processor, VEX RISC-V very often used. There's 64K of RAM, but the large blocks of RAM within this FPGA are weird in that if you start up, they're just blank, or actually they contain crap. Normally in an FPGA, if you use block RAM, you can specify the data in there, which is kind of important because you want your CPU to boot from something. So the biggest RAM here cannot do that. So I actually had to grab 4K of the other RAM and use that as a boot ROM. So that contains a little bit of code, and that uses the built-in SPI peripheral to talk to the boot flash to get the majority of the code, the main program, if you will. That then uses these peripherals in order to talk to the outside.
Sorry, so those 4K grams, so like that's not all RAM, like what is it?
So it's actually the other way around. The 4K RAM is block RAM. But the majority of the RAM in this FPGA, 128K bit, is what they call SP RAM, single port RAM. And it's a lot more limited, and one of those limitations is that you cannot initialize it. But you know, there's ways around that. Peripherals, there's not that many of them. There's UART because you need to printf debug. USB controller to talk to the host for the main communications, and of course GPIOs for the LEDs. So normally what happens is that the SPI can talk to the boot flash in order to load, etc. And the DUT pins are directly connected to the DUT flash, which is behind
you can minimize that DUT though.
Can I?
Okay. It will be on the way.
So to the main flash. So in this situation, by default, I can turn on the device and it'll see its flash and boot up and do happy things. One of the things you can do is use the mux to switch the SPI directly to the main flash, and that means that you can program the flash and read it, etc., etc. DUT will not be happy because it suddenly doesn't have a flash anymore, but you know, you just reset it, who cares? When you're done, you can reconnect the DUT to the flash, but you can also enable sniffer mode. And there is a block called SPI sniffer, and what it does is for each transaction, it'll record the first 5 bytes as well as the length of the entire transaction. So an SPI transaction to flash usually contains a command as the first byte, and then the 3 or 4 bytes after it are an address in the flash, which effectively says, hey, I want to start reading here. And then the length effectively can tell you how many bytes are read. So the SPI sniffer sniffs all that. It does that using the SPI clock as its clock, which was fairly tricky to do. But the nice thing is with this, it can support, I think, up to 58 megahertz or something, relatively high. Because that's in a different clock domain, it needs to do some clock domain crossing because you can't have 2 devices with different clocks talking to each other. And I also want it buffered. So there's an asynchronous FIFO, 256 entries. So, you know, if the USB is not available or doing something else, or the commands come in pretty quickly, then that's a little buffer. So the CPU can then read it out and send it over USB to the host, and the host can then figure out what's going on. So IP. So nice thing is you can just download CPUs. Just a shout out to what I used, VEX RISC-V. If you ever want to have a RISC-V on an FPGA, this thing is super flexible, can go all the way down to a microcontroller core that doesn't even have interrupts. I didn't need interrupts, so I never turned it on, and it just didn't build interrupt support. All the way to multi-core Linux capable chip support, all from more or less the same source. You can just configure it however you want. No to USB. I think it's Nitrogen USB, which is a project by Sylvain Munout, if you've ever heard of him. It's a nice little USB 1.1 stack. And the nice thing is that he also has C bindings for tiny USB. Tiny USB is great. Oh, it's a USB device stack, by the way. Don't try to make that be a host. And finally, the AUART came from Zip CPU. It's formally tested. It works. It's fine. So normally, if you do stuff like this build an SoC, there's the easy way. You can just use LightX, which is a Python tool set that just allows you to click together a bunch of things. I hear it's great. It's very easy. I was too lazy to pick the easy route. So I built it myself with all the fun that entails. Firmware, I also need firmware. We're not done yet. We've had the hardware, we've had the gateware, we still need the firmware. It's written in C because my Rust still is non-existent. As I said, it uses tiny USB. Tiny USB is great. If you have a USB device and you run tiny USB on it, then you can make it do everything. You can make it be a USB disk, you can make it be a serial port, you can make it be a media device, you can make it be all of that together as well. I'm just using the lower levels. This thing is just going to be a vendor-defined device. In other words, you plug it into your laptop, it'll do absolutely nothing until you run the software that comes along with it. It also controls the control mux via the USB. It'll send and receive SPI commands. So note that it doesn't know how Flash works. It just picks up commands from USB and sends it to the Flash and the other way around. And obviously the sniffer modes, it'll forward the packets that are incoming to the host. Software on the PC side, libUSB in order to talk to the thing. libUSB is great. And then because I needed something that can talk to Flash, but there's like a whole bunch of different Flash. There is a tool, it's normally a standalone tool called FlashROMs that has a database of like a whole bunch of different flashes in there, including the code how to talk to them. So what I did is I borrowed that code and just chopped off the head of it and connected that to my own thing. So the programmer is the FlashFriend and you know it can send SPI commands that way and my program is the bit that controls it on the other side that tells it to read and write, etc. And how exactly it reads and writes, it can figure that out itself. Okay, so this is the interior as it looks like. And the fun bit is, this is how the interior looks like as well. I'm going to mention it at some point, if I can open it. I'm so tempted to just tear it apart. So, and you see the interposer B here. But the nice thing is, did I put that here? Yeah. The nice thing is the reason why this is a 2.45 millimeter header and not a ZIF connector, which you might expect from a flat flex cable, is that I can put a bunch of headers on, a bunch of jumpers on there, and they'll connect the flash back to the DUT without me having to do anything. So this thing still works, even if the interposer is in between it. And that's also why I say that this is more or less throwaway, because if you don't use it, you just plug the header on there, you screw the thing shut, and you know it works. This is what it looks like if you actually connect to the FlashFriend. And I'm gonna do a demo live. Yes, tempting the demo gods. I'm gonna take it out as well. So this is the actual board. It's very small. Take the jumper off. That makes the microcontroller unhappy, but it's sleeping anyway. So just everybody quiet. Don't pick it up. Yeah, demo I'll do right now. And for that I need a laptop. And I am going to apologize to the people on Zoom. Well, maybe I can.
Oh yeah, it's already.
If I don't share it, then. Yeah, if I don't share it, maybe we can use the camera in order to.
Maybe on the video. Yeah.
I want to show the. It's on the top right there, the one that was covered. Yeah, it's still. There we go.
Okay, cool.
Wait.
And are we still sharing the thing? Because
Yeah,
maybe
stop
you need
sharing.
to stop that. That won't really
I mean, you
count.
can see both.
Okay,
Oh,
stop
there's-
sharing. Yeah, okay, see both. Oh, I just stopped.
Yeah, but like my presentation is more or less over, and I'm gonna plug the thing into the thing anyway. See if we can. I'm sure it'll be fine. See, batteries are a bit short, so I'm gonna.
Move that cable. Could be.
Yeah, my laptop is a bit. Oh no, wait. Wait.
It might have been the first time that actually on my phone was seen use.
No, it's
It must be a long while.
I've seen you use a bit a few times more often. So what I'll do is I'll plug it in. Let me grab myself a console first. Thank you. Okay.
Would it even be legible, the font? There we go.
It's a good call. Now I need to plug it in.
The lovely terminal. Whoever mounted it forgot to take the legs off and thought, nah, it's fine.
Okay, so what I have right now is can I?
Stop people from bumping into me.
Okay, let's begin with the sniffer mode. I want to see what it does when I press the button. Ah, it does a bunch of reads. Not sure. I hope that's visible. What it does is it reads some data from 46, 47, 48, and then it reads a whole bunch of data. And you saw that it actually takes a while and that it's doing the speaking. So it's actually reading the data from the flash while it is speaking. And then it reads one more byte from 49, 46, 47, 48, 49. Maybe that's a sort of command set or
Or
something.
maybe it's encoded in MP3 or some other file format.
Okay, let me show you. I'm going to record something. Now we're gonna see. Oh, that recorded a whole bunch. I wasn't even paying attention to that. That wasn't my intention. I am going to read to a file called flash.bin. It's not super fast, but it's fast enough. I don't take credit for the fancy progress bars.
It's a library.
That was all ChatGPT actually. Like fancy progress bars, I'll trust ChatGPT with. Okay, and then no, I'm gonna copy it. Okay, what we see is here a little bit of header, not that much. And then here, this is the first thing that the thing read 3 bytes from. And this is actually a page that is otherwise entirely empty. And if you record it like a few times, then you can see that this is the length of the wave that is recorded. And now we'll see why I whistled into that thing, because a whistle is a fairly nice sine wave, and you can see the pattern pop up here. You can see that the ASCII going up and down more or less. So this is the actual wave, and it is stored uncompressed as probably 8-bit data. And then after this, we'll have a whole bunch of nothing. And then after that, at the end of the 64 byte region, we have a bunch of other things. And I'll let you have a guess at what that is at the end. I want to go back because that 46, 47, 48, 49 bit was interesting. That takes too long. We'll say. Okay, that is at 46. So 11, 13, OA, OF. And after this one, it's shut down. Let's see if these are indeed commands. So this is 46. This is the first command. And I'll change that to OF. And we'll save. And I will write that with verify. Writing it, verification takes a bit longer because actually most of the flash is empty. Strangely, the thing only ever uses the first 64K of the flash. And looking at the pointers that are in there, it kind of hints at that this chip was made to control only 64K of flash, but 64K flash devices are not current anymore, and 512.
Usually you have on hand.
Yeah, well, use whatever is the cheapest, and I imagine that 512K is now the sweet spot. So let's see what happens. Let me go back. Wait, not Z, S. And if I'm right, then it should read the first byte and then immediately shut down. And yes, that's actually what's happening. It reads 46 and then it immediately shuts down.
So OF is the terminator? It terminates the...
OF is seemingly the shutdown command thing. Okay, let's...
But actually, so a question. So what does it mean when it says power down? Like that means that there's an SPI command sent?
There literally is an SPI command that says, okay, flash, go into low power mode. And you gotta send a command to...
the like the 0F or whatever opcode, that seems to be some kind of odd thing. Like it's an opcode in whatever microcontroller is on the epoxy to send out an SPI command to shut down the flash and then shut down the...
Exactly.
But this is crazy, right? Because that's like a lot of complicated logic.
So
for one opcode, so there's like a machine code instruction.
This is not machine code. I'm pretty sure of that because of some other reasons as well. This is just an interpreter for a very simplified language of like commands of what the thing does. There's actually two of them, one for the record button and one for the play button. And actually, if you swap those, the record button becomes the play button and the other way around.
But it's also very interesting because you would think that, like, what exactly are you winning by having a VM for this? Because, like, you need to have the interpreter for this bytecode, and you only need two functions, and both of them are doing something that's completely set in stone.
So what I imagine is that this thing can have multiple GPIOs connected to it, and it might want to do different things depending on the button that is pressed. Maybe play back different things.
Use the many toys with different...
Yeah, and I actually have a very good reason to think that, and I will tell you that because okay, I want to have hands of who wants to take a guess at what the data at the end of the flash was.
More wave files.
More wave files, okay.
A signature?
Signature, that's a good guess. I am very happy that
for other buttons that don't people do.
That's also a good guess. I'm very happy that I haven't heard anyone say firmware because, as you might have noticed, it doesn't load it when it wakes up. So whatever's there is not firmware. So actually, one of the things that are here is that there's a little table here, and if you read this little endian B46604, this is where one of the blocks at the end starts. And BD1804 is also a block. And I haven't shown this, but it actually reads the first 3 bytes when it is when you press the record button. So I was wondering what happens if you swap those. So if I make this 18BD, and this one I'll leave in place because it doesn't read it anyway. So what would happen? So let's save it and write it back. Verification takes a while. I actually still need to, I'll get to that later.
In fact, it takes a while, that's why there's a fancy progress bar.
Sorry?
Maybe defensive progress quite helps with the weight.
Yeah, for sure. Okay, so what does it do now if I record something? It says bleep. Wait, what?
Oh, it's like you press the cow and it says move kind of.
This is actually, this used to be the bleep bleep of the end of the recording. So what I think is that the bleep bleep is stored as a WAV file, namely the first WAV file. And what I just did is overwrite a pointer to some other WAV file that was in there. And that WAV file happened to be a train. So, with regards to the point that this is used for other things, there's your smoking gun.
I bet you there's toys that look exactly like that, but rather than record it and play back the sound, it has sounds on it.
I would think
picture of the choo-choo train.
Yeah.
maybe, yeah.
Picture
Anyway, so that is more or less the end of the presentation. Am I gonna?
So did you ever find? Okay, 2 questions. Did you ever find out what the microcontroller is?
No, because there's no firmware in Flash or anything that's. Let me quickly get the presentation back, and I'll just do the screen sharing the hacky way, as in I'll leave the camera on.
That's my question was complete. So of course there is one piece of this very nice setup missing, which is instead of writing back to the SPI
Mhm.
RAM or flash, you can reroute the, basically you can, how should I put this? So you can just have the FPGA answer SPI queries from the device under testing.
So I can, but you need fast memory for that, and you need lots of fast memory for that. In this particular case, it would have worked because the flash that is actually used is only 64K. But I also want to use this on other devices that have more flash, and there actually are. So, for instance, the Flash emulator does that, and it stores a Flash image in SDRAM and then retrieves it from there. The issue is more or less that you can't tell an SPI master to wait. Like with data, with NVMe, with whatever, you'll just get a command of, okay, please give me this sector, and then you have seconds to reply. So if you need to rummage through your backend in order to get the sector, that's perfectly fine. SPI needs that data, depending on the command that you use, the clock cycle after it sent the address.
Yeah, so you need an FPGA more block RAM.
Yeah. So actually, what I want to do is yeah, I'll go through that. So actually, that is the reason why I was talking about patches. So I do have enough memory to just store patches in. So for if at some point a certain region is read out that I am interested in changing, rather than read from the SPI RAM, I still have 64K of other RAM, so I could reroute it to read from there, and that would be my way to do this. But it's still a work in progress, as well as a few more things. I want to use compression. You saw that verification took a long time. Verification is reading out the flash, but in this particular case, it's mostly FFs because it's not very full. So what I want to do is use some RLE or some sliding window compression, etc., to just make those reads a lot faster, rather than say FF. The USB can just say, yeah, it's all Fs. Dual and quad mode.
Okay, so are you saying that it's the communication between the FPGA and PC that is the bottleneck?
I think so, because at the moment it's still USB 1.1, I think, so not the fastest. In theory, it can run a fair bit faster. So dual quad mode I want to have. Dual quad mode means that the thing uses 2 or even 4 wires in order to send back the data. In theory, I can sniff that as well, but in practice at the moment it's not really set up for that. I'm thinking about a faster FPGA because this FPGA is actually surprisingly slow. the 12 megahertz for the RISC-V core is because I can't get it to go any faster, and that is kind of sort of not what I was expecting. Even the SPI sniffer logic, it runs at 58 megahertz at the moment. That's its limit. I expected that to go way faster because it's not that much. It's just a simple state machine. It's just that this FPGA is unfortunately fairly slow. So I might do a redesign, but the nice thing is, because this is all more or less standard Verilog, I can just find and replace different FPGA and it'll mostly work. I won't have to modify the Verilog much. I wouldn't have to modify the firmware at all because it's still the same SoC. So yeah. The patching the firmware thing we already discussed a little bit about. I can implement it, but and the other thing is also I need to implement this as part of the sniffer, and I'm wondering how much slower they'll make the sniffer because more gates. A bit hard to say. Another option is to just say fuck it, use an MCU. MCU is USB 2.0. And it can read and write. I can't do the mux inside the MCU anymore, but maybe an external chip will work. The sniffing probably works as well if you pick the right MCU. But the time of TOC TOU is kind of sort of impossible because you need a very fast reaction time to change that stuff on the fly. So I'm not sure. Like the other side of the coin is, you saw what I did with this now. This is perfectly sufficient for hacking toys, etc. And I haven't run into a situation where this doesn't suffice, mostly because I finished this like 2 days ago. So, but it's kind of like we'll burn that bridge when we get to it. Okay, thank you all for listening. I hope this was interesting.